All right, so in this section, we're going to take a look at just generally and briefly some of the acid-base properties of both oxides and hydroxides. Um, and there's a really good summary here in this table, periodic table that's slightly edited. And it's color-coded based on the acidic, basic, or amphoteric nature of the oxides of both metals, non-metals, and also the metalloids. So generally, what we're going to see is that the ones in blue, right? Those are your basic oxides. So these are oxides of the group 1, typically in the group 2 metal oxides. These will react with water to form metal hydroxides, right? So because they form hydroxides, that makes them bases. So for instance, let's say sodium hydroxide can react with water to produce sodium hydroxide, and that obviously would be a base. On the other side of the periodic table, you'll see the squares that are in purple. Those are acidic ones. And those are your non-metal oxides. Those tend to react with water to produce acids. So for instance, carbon dioxide in the air can react with water to produce carbonic acid. Right, and I mentioned this previously. Whenever you have carbon dioxide dissolved in water, it is going to be an acidic solution because of the carbonic acid that's produced. Other types of oxides, non-metal oxides like sulfur trioxide, this is a major source of pollution, like acid rain, for instance, that can react with water, rainwater, for example, to produce sulfuric acid. So typically, your metal oxides are basic to form metal hydroxides when they react with water. Your non-metal oxides react with water to produce acids. They tend to be acidic. If you react your acidic oxides and your basic or your bases, those would be your typical, or they would resemble your typical normal acid-base neutralization reactions where a salt and water is produced at the end. What you'll also see on this table is that there are some orange shaded boxes, and these are oxides that are amphoteric, and meaning that they can behave as both acids and bases. So for example, aluminum oxide, Al2O3, which is over here, can behave as both an acid or it can behave as a base. So in the case of the Al2O3, right, it just depends on what it is that it's reacting with. So in one instance, it can act as an acid. In another instance, it can act as a base. This is a typo here in your slide. This is showing how it acts as a base when it reacts with an acid. This is hydrochloric acid. And the second one is showing how it can act as an acid when it reacts with sodium hydroxide, which is a base. Right, so it's very unusual in that, but there are other examples of oxides that can behave as both. The hydroxides, also all of the alkali and the alkaline earth metal hydroxide. So alkali metals, these are in group 1. So lithium, sodium, potassium, rubidium, cesium, etc. And then the alkaline earth, these are in group 2. Okay, so things like magnesium, calcium, strontium, barium, those are basic, with the exception of beryllium hydroxide. And there are lots of examples of hydroxides that can be amphoteric as well, beryllium hydroxide being a good example of where it can act or can behave as both or either an acid or a base, depending on what it is that it is reacting with. So it depends on the environment that it is subjected to. All right, so in this last section, we're going to take a look at a new definition of acids and bases. So as a quick reminder, let's just review the two previous examples, the two previous definitions of acids and bases, we would have talked about the Arrhenius definition of acids and bases a long time ago, maybe in Gen Chem 1. So according to Arrhenius, an acid is a substance that produces H plus ions, hydrogen ions, protons, when dissolved in water. Whereas an Arrhenius base is something that produces hydroxide ions, OH minus, when dissolved in water. We've also seen the Bronsted-Lowry definition that we focused on a lot in this section. And according to the Bronsted-Lowry definition, an acid is a proton, acids are proton donors. So remember, proton is H plus. Proton donors, whereas a base, a Bronsted-Lowry base, are proton acceptors. Okay, they take in, they accept protons. So the third definition of acids and bases is a new one. It's called a Lewis acid and a Lewis base. And just like the first two, this is named after a person. Lewis was his last name. And according to the Lewis acid-base theory, this has to do with pairs of electrons, right? So a Lewis base is a substance that donates pairs of electrons, whereas a Lewis acid is a substance that can accept a pair of electrons, right? So in contrast to Bronsted-Lowry, where we looked at the movement or the ability of something to donate or to accept protons, now we're looking at the ability of something to donate or accept pairs of electrons. So the way that I remember this is that a Lewis acid, the A here for acid, accepts, right? A for acid, A for accepts a pair of electrons, and then obviously the other would be the base. So the base then would donate a pair of electrons. So a good example of this would be the reaction between boron trifluoride, BF3, and ammonia, right? So if you were to draw the Lewis structures, which are going to be very helpful for these, and by the way, they're Lewis structures, and we're looking at Lewis acids and bases. What you will notice is that the boron trifluoride with the central boron has 3 electron groups around it. And what that means is that it is sp2 hybridized, which means that it has an unoccupied p orbital and an unhybridized p orbital that is shown here that is empty, which means that there's space for it to accept a pair of electrons. Well, in ammonia, NH3, when you draw the Lewis structure, you will see that it has a lone pair of electrons on the end. So it can actually donate that pair of electrons to the boron that can accept it. And by doing that, it actually forms a brand new bond between the N and the B. That type of bond is called a coordinate covalent bond. Sometimes it's called a dative bond. You don't see that term very often, but it has been used. And that results from an atom donating a pair of electrons, another atom accepting a pair of electrons. So when you see that donating and accepting pairs of electrons, that means that we have an acid-base reaction occurring, and that's a Lewis or an example of a Lewis acid-base reaction. So the Lewis acid in this case would be the boron trifluoride that accepts the pair of electrons, whereas the Lewis base would be the ammonia that donates a pair of electrons. Okay, so in all of these examples that you're going to see, it is going to be very useful if you actually if you draw out as best as you can, draw out the Lewis structures, because it is going to be a lot easier to see where the electrons are coming from and where they're going. Generally, what you're going to see is that your metals are things that tend to be electron deficient, and they tend to be then the Lewis acids that can accept pairs of electrons, whereas the other thing will be the Lewis base, typically the nonmetal that has lone pairs on it. Those would be able to donate those lone pairs and act then as the Lewis base. Right, so this is a new, and I'm fairly certain we haven't seen Lewis acids and bases before. We're introducing it now just briefly. You're going to see this a lot, especially if you go into organic chemistry, where they invoke the Lewis acid base theory to describe the behavior and to predict the behavior of organic molecules.